Hello, and welcome to workshop number 1, piston head analysis for the patron student edition in the finite element method class. What we're going to try to do is analyze the different patterns and the meshing of a piston head. We will start by creating a new database. We'll call it piston DB. Let's start it. Our database has been created, and what we're gonna do next is just check that the new model preferences are set to our desires, which they are. We want the tolerance to be based on the model, the approximate maximum to be 10, the code we want an asterisk, and our analysis will be structural. After creating our database, what we're going to try to do now is import our geometry. So we're going to go to File, Import. Now it's important to make sure that we have a parasolid file, XMT, which we do. We're going to select our geometry now. The geometry that we need was provided for us. It's called Piston XMT, and we're going to hit Apply. The file import has been successful. We're going to click OK. After this, we're going to want the smooth shaded on the display area. We're going to click that, and we're going to start rotating around, and we're going to see our piston head has been correctly imported. Next thing we're going to do, we're going to create a finite element mesh. Under Elements, we're going to select the action Create Object Mesh. It's going to be a solid. Most of the settings will remain the same. We just have to make sure we have the TET mesh mesher. In the input list, we're going to select the entire model. And it's important to not check automatic calculation, just to make sure the values don't go haywire. Also, the value of 0.5 will be set, and after that we just hit Apply. The mesh has been created. Our next step is going to be to create the constraints. It's pretty much a nodal displacement constraint, and what we're going to do is we're going to call it fixed in the new set name. We're going to go to input data and just restrict all linear translations. Click OK in that window. We're going to select the application region, and what we want to do is select surface or face options, and we're going to select the inner faces of our rings. We're going to select it and click Add. Then we're going to select the other face and click Add as well. After this, we're simply going to click OK and then Apply. Next up, we're going to try to create for the simulation the piston pressure. We're going to select on an element uniform, on a uniform element, and we're going to call it piston pressure. The target element type is going to be 3D. On our input data, we're going to select 1200 pressure. Click OK on that window. Our application region is going to be a solid face. And we're going to select the top of the piston, which is already selected and added. I'm going to click OK on that. After the geometry has been selected, the pressure has been set, and the name has been properly set because we can't have spaces there, we're going to click Apply on that. As you can see, now we have our pressure being applied. What we have to do now is create our material. So we're going to go to materials, create an isotropic manual input. We don't have any existing material, so we're going to call this steel. And we're going to go straight into the input properties, and what we're going to select is the elastic modulus. We're going to select it at 30 times 10 to the 6th, and the Piston ratio 0.3. We're going to click OK in that window. Then we're going to go straight and just apply what we've done, and our material has been correctly uploaded. Next up, we're going to create our element properties for a solid. So we're going to click here on solid, create a 3D object, solid type. We're going to call this piston, and we're going to go straight into our input properties. And here what we're going to select is the material name. I'm going to click on our material list, and steel pops right up, so we select that. After that, we click OK, and we are going to select the application region, and we're going to select just the entire piston head, add it on, and click OK. Once that's all set, we just check our options to see they match, and it's homogeneous and standard formulation. We're going to hit apply, and the piston, our property set piston has been created. Next up, we're going to check our load cases just to make sure there's no mistake in what we've been doing. We're going to go to load B and BCs and create load cases. Instead of create, we're going to go to modify. We're going to click our default existing load cases. So what we're trying to check is that the loads are assigned correctly, our fixed displacement and the piston pressure, the scales that we want. And once we make sure it matches, we're just going to cancel, and that's basically it for this step. After that, we're going to run our analysis. So for one of our final steps, we're going to analyze the entire model over a full run, which will give us a wide variety of files that'll clear up our results. So the job name has to be the same as your database, and the first thing we're going to do is go into your translation parameters, make sure everything's in check. Wouldn't miss anything. We're going to click OK on that window. We're going to go to our solution type, and it's very important that we have a linear static solution type for our problem. We don't have to mess with the solution parameters or any other areas in this window. And basically, after we've done that, we're just gonna apply our analysis onto the model. A correction had to be made to the previous meshing technique due to lack of the full program and only having the student edition. We had to reduce the mesh components, so we went from a TET 10 mesh to a TET 4 mesh. What we're seeing now is a quantity in von Mises stress, the tensor section, and as we can see, the greater stress logically is at the center of the top of the head, and in the inside we can see the outer regions are most stressed due to the lack of geometrical presence in the pass holes. Moving on, we go right into the displacement, the translational deformation results, and what we can see from the model is that the top head obviously has been bolted in due to the increased pressure. The side flaps have been extended quite a bit because, of course, our fixtures are set as we said earlier, in the pinholes, and there's not much deformation shown in the mesh at the pinholes. It's mostly on the sides, without a pinhole. In conclusion, from the stresses collected in this analysis, we can see that under constant pressure on the top of the head, a piston will present this type of fringe deformation, expressed in the colors on the right, numerically, but also we can see the actual deformation shown numerically here, which gives us a 4.26 times 10 to the second patching units, and we can check it out right here. We can see that deformation right there, the difference between the edges.